In this section, we're going to look at solving equations by factoring. And specifically, we're going to focus on quadratic equations, although anything that could be factored could be solved this way. So what is a factored equation versus a standard form of a quadratic? So a standard form might look like this, something like 0 equals x squared plus 8x plus 15. That's an example of a quadratic equation because the highest power is 2 on the x in standard form. A factored form of the same equation would look like this if it factors. So in this case, x squared plus 8x plus 15 does factor into a product of two binomials. If we split the 15 into 5 and 3, then the outer and inner terms will add to 8x, so that works. So this is an example of factored form of an equation. Now, why would you want to factor it to solve it? Well, if you look at the standard form, it's kind of hard to solve for x because there's two x's. There's one there and there's one there. So how do you get it by itself? Right? That's the tricky part. It's not as simple as with a linear equation. But with a factored form equation, there's a nice property called this zero factor property that allows us to very easily solve this equation. Okay, so the goal in this example is we're going to solve that equation for x, meaning we want to find all the values of x that make this equation true. That's the goal. Well, I haven't changed anything just by factoring it. All I did was factor it. But if I was to refoil the right side, it would look just like this. Okay, now the idea behind solving an equation by factoring is that a product, if you have a product of two things, for example, let's say a times b, and you know that when you multiply a times b, you get 0. Well, the only way you can multiply two things and get 0 is if one of the two factors is 0, because 0 times anything is 0. So this equation is true if either a equals 0 or if b equals 0. If either of those things are true, then this equation is true. So that same idea works here. Okay, if this first factor, x plus 5, is equal to 0, x plus 5, or if the second factor, x plus 3, is equal to 0, if either of those things is true, then their product is going to also equal 0. And this leads us to two simple linear equations that are very easy to solve. Okay, so those are actually the two solutions to this equation. Okay, and it's very easy to check. We just plug them in to the original equation. So I'm going to plug in, first let's check x equals -5 and see if it works. So -5 squared plus 8 times -5 plus 15. Well, -5 squared is 25. 8 times -5 is -40 plus 15. Yeah, 25 minus 40 is -15. So that is, in fact, 0. And the same thing can be shown for x equals -3. Okay, so the zero factor property, that's the important part. If a times b equals 0, then either a equals 0, b equals 0, or both. So if you're trying to find all the solutions to an equation where you have a product on one side, like a factored, notice all of these are factored product on one side and 0 on the other side. Now notice it only makes sense if the other side is 0. Well then, if either of those two factors equals 0, then the original equation is true. Okay, so here's a couple of straightforward examples. If 3 times x equals 0, well, there's really two ways to do this. You could set each of the two factors equal to 0 and say either 3 equals 0 or x equals 0. 3 equals 0 makes no sense, so we just cross that off. And x equals 0 is the only real solution. Alternately, you could divide both sides by 3 and get x equals 0 as well, because 0 divided by 3 is 0. Okay, here I would probably do that. Divide both sides by this constant 5. So x plus 2 equals 0 divided by 5. Well, 0 divided by 5 is 0. So you get x equals -2. So if an equation is factored, all you do is set each factor equal to 0 and solve. Now this only works if you have 0 on the right side though. So pause the video, try these next two. I like to write it like this, and I recommend you do as well. actually write one factor equals 0 and the other factor equals 0, and then solve each of those equations for x, and that gives you your two solutions. Here we'll have x minus 3 equals 0 and x minus 7 equals 0, so x equals 3 or 7. We'll solve this equation. Okay, again, pause the video and try these two. These are already in factored form, which makes them easier. So in this one, if we set x plus 17 equal to 0, we get x equals negative 17. That's one solution. And over here, if I set 2x minus 4 equal to 0, oh, there's a tiny bit more work. Okay, so 2x equals 4. Dividing both sides by 2, we get x equals 2. Here, I would divide both sides by 3 to eliminate the 3 first. You don't really even need to show that step. So then we get x minus 4 equals 0, or 5x plus 8 equals 0. So x is either 4 or 5x is negative 8. So x is negative 8/5. And those are the two answers to that equation. Okay, and then it goes on. Your original equation could have more than 2 factors. It could have 22 factors, right? If it's factored, which this is, you just follow the same process. Set each factor equal to 0 and solve. So there's one equation, a second equation, and a third equation. And we solve each of those for x. Okay, so that is how you solve an equation by factoring. You set the polynomial equal to 0, factor it, and then set each of the factors equal to 0 and solve, and then you can check your answers if you are unsure. Okay, so this is an example where there's a little bit more work because it's not already factored. So first you have to factor this side. Now, step 1 is already done. One side is already equal to 0, so that's fine. We don't have to do anything there. Now let's see if it factors. 28 we could break into 7 and 4. I like that because between 7 and 4, I think we can get a 3. So let's put x, let's do plus 7 because this is plus 3, and minus 4. All right, that way when you refoil, you would get x squared minus 4x for your outside terms. Inside term is plus 7x. Last term is minus 28. So that does add to plus 3x. And then you set each factor from here equal to 0. So x plus 7 equals 0, or x minus 4 equals 0. So x is either negative 7 or 4. Okay? And as you watch the video, make sure you pause and try each one. And then if you're not sure how to start, or if you get stuck, or if you finish and you want to check, then restart the video. So in this next example, it is a quadratic equation because we have an x squared term, an x term, and a constant term. But notice it's not equal to 0 on one side. So we actually do have to make it equal to 0 on one side. To do that, I'm going to move the 23x over to the left. So that'll give us 2x squared minus 23x plus 30 equals 0. And then we have to try and factor this. Hopefully it's factorable. See, the first term needs to become 2x squared. So let's break that into 2x and x. And then we'll play around with this a little bit. 30, let's see, if we put 6 and 5, I'm not sure that that will add to 23. So we could try 10 and 3. Let's try putting a 10 there and a 3 there. See, because then that's going to give me 2x times 10 is 20x, and 3x is 3x. So if I make both of these negative, that should work. Then we set each factor equal to 0 and solve for x. So x is either 3/2 or x equals 10. Both of those should solve this original equation. I haven't checked any in a while, so let's go ahead and check the 3/2. Let's check 3/2. So I'm going to plug that into the original equation. 2 times x squared is 3/2 squared plus 30. Hopefully that equals, question mark, 23x. So 23 times 3/2. So 3/2 squared, 3 times 3 is 9. 2 times 2 is 4, plus 30. Does that equal, let's see, 23 times 2 is 46, and that's going to be over, no, sorry, 23 times 3. We need to multiply everything times 3. So 2 times 3 is 6, 3 times 3 is 9, that's over 2. So let's see, this 2 and 4, I can take a 2 out of both of those. So we have 9/2 plus 30. Let's write 30 as 60 over 2. And then, yes, it's pretty obvious that 9 plus 60 is 69/2. So that's just to check one of them. You could check the other one just as easily. Okay, this next one, 6x cubed. Interesting, it's a cubic. Minus 9x squared minus 6x equals 0. So for that one, it's not a quadratic. It's actually called a cubic equation because the highest power of x is 3. But we can take out a greatest common factor. So it looks like I can take a 3 and an x out of everything, and that gets me started on factoring. So then I have 2x squared minus 3x minus 2. Okay, so at this part I could either go ahead and set each of these factors equal to 0, or I could keep trying to factor more. I'm going to keep trying to factor more and see if I can go further. So let's set the 3x, well, the 3x we'll just copy. Let's see if this quadratic part continues to factor. So I'm factoring this part. The 2x squared will have to factor into 2x and x. Then I need to get a 2 here. So I'm going to have to break this 2 into 2 and 1. So I'm going to put a 2 here and a 1 here. I want the middle term to be negative 3x, so I need to put a negative here so that 2x times negative 2x is negative 4, and a plus there, plus 1x is negative 3x. So that'll work. So now I've got 3 factors. I've got 3x equals 0, 2x plus 1 equals 0, and x minus 2 equals 0. So x is either 0, negative 1/2, or 2. Oops. Supposed to say 0. Okay. So you can, of course, work some applied problems using the same process. Some applied problems can be solved by factoring, and in the next section we'll learn another way to solve quadratic equations, specifically for quadratics that don't factor, because of course not all quadratics factor. So the revenue from selling handmade pottery at an art festival can be modeled by R of P equals P, let's copy it down here, R of P equals P times 100 minus 3P. It says where R of P represents the revenue in dollars from selling P pieces of pottery. So P is the number of pieces of pottery, and R is the number of the amount of revenue in dollars that you make at an art festival. So find the number of pieces of pottery that must be sold to have a revenue of $700. So if it says find the number of pieces of pottery, that translates to find P, because P represents the number of pieces of pottery. And if you want to have a revenue of 700, that means R of P must equal 700. So I'm going to set R of P right here equal to 700. So I'll have 700 equals P times 100 minus 3P. So I'm just replacing this R of P by 700. And now we want to solve this for P, because we're trying to find the number of pieces of pottery that give us a revenue of 700. Well, when you first look at this equation, let's make that blue. When you first look at this, it probably does not look like a quadratic. And in fact, you may say, well, it's already factored on one side. That's true, but the other side is not 0. So we've got to move the 700 over. So that'll give us p times 100 minus 3p minus 700. Okay, that's good, but I still can't factor anymore. So I'm going to have to distribute, I can't factor anything out of this term and this term. 700 has nothing in common with p times 100 minus 3p. So I'm going to have to distribute this p out and then try to factor. So if I distribute the p, I have 100p minus 3p squared minus 700. Let's rearrange the terms and put them in the order we normally see them in, which would be more like this. Negative 3p squared plus 100p minus 700. Now if you're like me and you don't like to have a negative in front of your first term, let's just multiply both sides by -1 to eliminate that negative. So on the left I'll still have 0. Then -1 times negative 3p squared is positive 3p squared. -1 times 100p is negative 100p. And then plus 700. Okay. I think that might just be easier to factor. So let's see. The 3p squared only is going to factor into 3p and 1. It's the only way to do it. Now we want the last term to multiply to 700 and our middle term to add to negative 100. So let's see. 700, I could break it into, let's do some scratch work over here. 70 and 10. Which strikes me as, yeah, that might work because 70 and 3, somehow I may be able to get 100 out of that. So what if I put, let's try putting 70 there and 10 there. Now they're going to multiply to a positive and add to a negative. So regardless, both of those have to be negative. Now if I look at this, it's probably not going to work because 3 times 70 is 210. So my outside term is negative 210p, and my inside term is negative 10p. So that doesn't work. Let's back up a little bit. Let's try putting the, let's see, let's put p minus 10 here. Let's see, that will give me, for my outside term, 3p times negative 10 is negative 30p. Then I would want, yeah, this might work, because then I can put the 70 here, so negative 30p, then my inside term would be negative 70p, which does add to negative 100p. So that works, nice. So then let's set each factor equal to 0. So 3p minus 70 equals 0, and p minus 10 equals 0. So I'm going to get two answers. P equals 10, 3p equals 70, so p is 70 divided by 3. Now because this is an applied problem and p represents number of pieces of pottery, it really only makes sense to actually figure out what this decimal is and then round up. So 70 divided by 3, 70 divided by 3 is 23.333. Well, you can't make 23 1/3 pieces of pottery, so I would round up to 24 in that example. So let's read the question again. It says, find the number of pieces of pottery that must be sold, that's supposed to say sold, to have a revenue of $700. So it looks like if they sell either 10 pieces or 23, about 24 pieces, either way, they'll make $700, which is kind of interesting. Okay, so let's circle these. So if they sell either 10 or about 24, that's a rough estimate there since we got a decimal, pieces of pottery, the revenue will be $700. Which sounds a little bit strange. How come you would sell more and still make the same amount of revenue? Maybe, who knows, maybe they discounted the pottery or something at some point. So, okay, so that's how you solve equations or quadratic equations specifically by factoring. And then we'll look next at how to solve, how to how to solve quadratic equations in two other ways.